Ladies and gentlemen, and dear colleagues, good morning. Let me begin. My name is Olga Zaitceva, and I have a master's degree in chemical engineering. I'm a researcher in Russian Academy of Science, and I want to talk about the structural changes of asphaltenes during hydroconversion. The tendency towards the use of the heavy petroleum feedstock and the necessity of increasing the efficiency of oil refining require development of new additional process involving the structural reduction of macromolecular petroleum component to produce light fraction. One of the major problems in deeper processing of heavy petroleum feedstock is the high impurity content, such as sulfur, nitrogen, and vanadium and nickel that are concentrated in asphaltene fractions. First of all, this is due to the catalyst deactivations. Asphaltenes are the heaviest and most complex molecules that are presented in petroleum and contain in heavy petroleum feedstock and vacuum residue in a significant amount. These constituents of petroleum act as co-precursors, and they are precipitated on the catalyst surface and block the pore mouth. They can limit the maximum level of feedstock conversion. Thus, a deeper knowledge of their properties, such as molecular and colloidal structures and properties, can result in better comprehension of their behavior in hydroprocessing to increase the efficiency of refining and control their conversion. The solution of this problem most effectively implement in hydroconversion process in the presence of nano-sized catalyst particles that are synthesized in situ in the reaction zone. Water-soluble salts of catalytically active metals are used for preparation of catalyst precursors. Introduction of salts as emulsions is followed by conversion to the slurry in heat treatment. Different feedstock, including heavy oils, petroleum residues, and bitumens, can be used because catalyst is not deactivated due to precipitation of asphaltenes and heavy metals. Two steps of investigation of changes in the characteristics of molecular structure and physical chemical properties of asphaltenes were carried out. Structural changes in asphaltenes at various hydroconversion temperature were studied during first experimental session. A different number of asphaltene conversion stages in the reaction zone during second session. The recycling of the unconverted vacuum residue provides an increase in the number of asphaltene conversion stages in the reaction medium. After each experiment, the hydroconversion products was fractionated by atmospheric vacuum distillation. The distillation residue, the fraction more than 520 Celsius, was mixed with the fresh feedstock, and this mixture was sent to the next hydroconversion stage. During hydroconversion experiments with the recycling of the vacuum distillation residue, the conversion of feedstock components, including asphaltenes, was carried out in 6 steps. Structural characteristic of asphaltenes from initial vacuum residue and its hydroconversion products was studied in this work. It should be noted that as a molecular or colloidal asphaltene structures are known, such as nanoaggregates or cluster of aggregates. Their existence is dependent on environmental conditions. In this work, we studied structural types of asphaltene molecules with single polycyclic aromatic hydrocarbon ring system. The structural parameters of asphaltene molecules were calculated according to the method of structural group analysis, which is based on the combined use of elemental analysis results, average molecular weight, and distribution of hydrogen atom. One of the main features is the non-monotonic character of changes in molecular weight. According to this, it has been noted to two characteristic temperature ranges in which molecular weight growth is observed due to increase in asphaltene aromaticity, and two transitional states in which a significant fall in molecular weight takes place. A comparison of the ring composition characteristics indicates a prevalence of hydrogenation reactions at lower temperatures, and temperature increase above 414 Celsius leads to a significant growth in the cracking and cyclohexane ring opening reactions. In high temperature ranges, the ratio of the amount of aromatic rings to the total of rings approaches 1. Several features are observed by considering the ratio between aromatic and saturated carbon atoms. It's found that lower extent of suppression of hydrogenation reactions provides stability of the condensed aromatic core. Distribution of the amount of carbon atoms in naphthenic and paraffinic structures indicates that decrease in saturated structures at low temperature is mainly due to dealkylation. In the high temperature region, the decrease in the proportion of saturated structures linked to cracking, dehydrogenation, and cyclohexane ring opening reaction. As hydroconversion temperature increases to 414 Celsius and above, the proportion of short alkyl chains decreases relative to naphthenic structures that surround the aromatic core, and number of these naphthenic rings decreases as well. It contributes to the nucleation and growth in the asphaltene phase of a mesophase and influence the significant increase in the yield of coke. Thus, the comparison of the structural parameters allows us to show a scheme of transformation of asphaltene molecular structures depending on hydroconversion temperature. Structural parameters vary in a discrete manner, passing through a step of transitional state in which system is the most susceptible to the action of external factor. Changes in asphaltene morphology depending on hydroconversion temperature were studied by using SEM. Investigation of changes in asphaltene morphology confirms the main features of the structural transformations of asphaltenes, which were established by a structural group analysis of asphaltene molecules. It shows that the quality rearrangement of the asphaltene molecular structure by passing through the transitional state where the system is most active leads to quality changes in the asphaltene morphology and change of colloidal chemical structure of the system. It's known the collective interaction between macromolecular components occur in petroleum dispersed system, forming the complex structural units. Moreover, asphaltene aggregates are reversible supramolecular structures that are able to destruction due to external factors. In addition to the temperature, synthesis of catalytically active phase molybdenum disulfide in situ in the reaction zone from emulsions followed by the conversion to the slurry in heat treatment influences the destruction of complex structural units and change in asphaltene morphology. Special redistribution of macromolecular components and colloidal asphaltene structures occurs in the step of emulsion formation. Asphaltenes are as close as possible to the surface of the synthesized catalyst particles, forming structured interfacial layer around water globules. Intensive evaporation of water from the solution and crystallization of salts in hydroconversion are accompanied macro-explosions of emulsions droplets, and it leads to additional dispersion of colloidal asphaltene structures and desorption of resins from their surface. The investigation results of asphaltene molecular structure show that changes in molecular weight, depending on the number of asphaltene conversion stages, is at temperature variation and non-monotonic in character, passing through a step of transitional state. By structural group analysis, the structural parameters of asphaltene molecules were determined. The result confirmed the occurrence of structural transformations connected with dealkylation and cyclohexane opening reaction via scission of carbon heteroatom bonds. The condensed naphthenic aromatic core is characterized by relative stability in the range from R0 to R3 experiments. But a further increase in the number of conversion stages contributes to rise in the rate of dealkylation reactions, also decrease in the number of aromatic structures and nitrogen and sulfur contents. The changes in the structural parameters at each step of a transitional state are due to the prevalence of characteristic reactions, where similar as the variation of temperature and changes in the number of conversion stages. However, there is significant difference between structural transformation of asphaltenes depending on various process parameters. The implementation of several asphaltene conversion stages in the reaction medium make it possible to change the molecular weight and structural parameters, mainly as a result of destruction of cyclic fragments, including the most stable heteroaromatic structures. At the same time, stability of the condensed aromatic core was identified at variation temperature. As increase in the number of asphaltene conversion stages, sulfur rather than nitrogen is easier removed by cracking of the most stable heteroaromatic structures having low reactivity. During the further destruction of aromatic structures, the removal of sulfur and nitrogen atoms occurs at the same rate. In various ways of enhancing the feedstock conversion, the character of changes in aromaticity of asphaltene molecules is also different. Even in continuous growth of aromaticity molecules occurs at increase in hydroconversion temperature. However, aromaticity of asphaltene changes in a narrow range with varying the number of conversion stages. As the number of asphaltene conversion stages is greater, the aromaticity of molecules is lower. This feature explains the possibility of increasing the feedstock conversion with low condensation product formations in experiments with the recycling. At the same time, a significant growth of coke formation is observed in the reaction medium by increasing the temperature above 414 Celsius. One of the most important results in terms of chemical colloidal properties control and increasing the efficiency of process is discrete manner of changes in asphaltene molecules depending on different process conditions. Hydroconversion parameter intervals were established where the system is most active and action on the petroleum system will be most favorable to regulation of structural transformations of macromolecular components and increase the conversion level with low coke formation. Thank you for your attention.